last time, we derived the phonon-phonon interaction by this third-order potential beyond harmonic approximations. And so we have these processes which involve this creation of three phonons out of a vacuum, or destruction of three phonons, and also one phonon splits into two phonons, or these two phonons get merged into the single phonon. So, these two processes involving the three phonons generated or destructed at the same time are called virtual processes. And they are virtual because they are not a real event, because the energy is not conserved. So this phenomena cannot happen alone. Okay? And so is the second processes. But the third and the fourth processes are real processes because the energy of phonons at this interaction vertex point can be conserved. Okay, so these two processes are real. Okay, so they can happen in the real physical processes. But we can go higher order in H3 to actually say combine this virtual or real processes into the four different real higher order processes that we will discuss in just a moment. Okay, so to discuss these processes, we need to conserve the momentum. Okay, because as we already derived last time, at interaction vertex point, this crystal momentum should be conserved, and therefore we have this crystal delta function, okay, which tells you that this delta as a function of this three momentum sum gives you 1 if the sum of the three momentum gives you this reciprocal lattice vector G, where G could be either 0 or non-zero. For the processes that involve 0G, or reciprocal lattice vector being 0, is called the normal processes, and we will come back to this just a moment. And for a finite G value or G vector involving this crystal momentum conservation, and we call the Umklapp processes or U processes. And the normal process is also called the M processes. Okay, so in your solid state 1, so you should be familiar with these terms that in some cases we get normal processes, and in other cases we get Umklapp processes. And I will explain to you what we mean by the Umklapp processes later, but so let's just do perturbation theory to estimate the energy change due to this third order potential. And if we consider just the first order in H3, and in quantum mechanics you know that you could just evaluate this expectation value of the H3 sandwiched by this many body occupation number of states, and you know very well that this single H3 would change the number of bosons, right? Because you either create or destroy three bosons or three phonons, or you change the phonon number by 1. Either you create you split a single phonon into 2, or you merge two phonons into 1. So in either case you change the phonon number in your final state, and therefore the phonon number, occupation number in the final state would not be the same as the initial state. And from this orthogonal normalization condition, you know very well that this matrix element vanishes. Okay, so we don't have any first order correction to the energy because of the orthogonal properties of this initial and final state. But we can go one order higher, which means that we go to the second order in perturbation theory, and therefore we know that from quantum mechanics that there will be intermediate states Nj involving which mediate this H3 second time, because you got the second order. So initial state is Ni, and then the system goes to the excited state or intermediate state Nj, and then later it jumps back to this Ni. Okay, so initial and final state is the same, but intermediate state is different. So from quantum mechanics, we know that the correction to the energy is given by the second order in perturbation theory, where the energy denominator is given by the energy difference between state I and the state J, where I refers to the initial and final state, but J refers to the intermediate state. And in the numerator, you get the product of those two matrix elements, which is complex conjugate to one another, to each other. So you get, H3 sandwiched by Ni and J times the Hermitian conjugate, or complex conjugate of this term. So you get a square of this matrix element, and in general, this is non-zero. Okay? So in other words, we could discuss the consequence of the second order in perturbation theory in H3, so that we could lead to several important conclusions, including how to reach the thermal equilibrium, how to explain the thermal conductivity, and thermal expansion of solids. And this is the diagrams that are associated with those second order processes. You can see that if we square the H3, and you could simply just cut this diagram into two, and so that the left side and the right side of this vertical line corresponds to this virtual process number 1 and virtual process number 2. So if you merge these two on both sides, you get this bubble diagram like this. And likewise, if you merge the which diagram is this? The third one. Okay, so you got a combination of this third and the fourth diagram, and if you simply just connect this intermediate states, you get the third bubble. Okay, and the second one is the combination of this processes twice. Okay, and the fourth one, of course, is the copy of this first and second processes. So when you combine these four processes in the linear turning H twice, you get all different combinations of this initial and final state, and therefore take two copies of these virtual processes, you get the real processes. Okay, so all these four processes are real because the energy could be conserved. So that out of vacuum you create 3 phonons, but these 3 phonons are annihilated later time. Okay, likewise this and that. Of course, the 3 phonons could be merged into the vacuum, but then vacuum can actually create another 3 phonons. Okay, so the energy is still conserved. Okay, so we could understand many solid-state phenomena based on this kind of second-order processes of the H3. In particular, we could explain this thermal conductivity due to phonon in ordinary solid-state materials. So let's just review this classical thermal conductivity in your general physics 1. For example, this mean-free path. Mean-free path is the length scale below which you don't get any scattering. Okay, so the scattering happens when this length scale is actually over this L x in the x direction, for example, and this is given by the scattering time times the velocity along that direction, right, in the classical statistical mechanics. And we could discuss the heat flow of an object from, say, one place to another along, say, the x direction. So the heat flow is the time rate of the energy per unit area. Okay, so, and in, say, standard statistical mechanics, it is defined by this temperature gradient, dx dt dx, which is the temperature variations along this direction, the slope of this temperature the temperature gradients, temperature change per unit length, and multiplied by a constant called thermal conductivity, kappa times minus sign, because this is just a standard definition of the heat flow. And you could check your classical stat mech, and you know that this is given by the number density of a particle times the square, the mean square of your velocity, and the heat capacity per particle n times the scattering time or mean free time. And if we are dealing with the isotropic three-dimensional system, this Vx squared, taking the expression value, is actually 1/3 of this V squared, where V squared could be, is a sum over all three directions. And then instead, in stat mech, you know that this kappa, which we call this classical thermal conductivity, is given by 1/3 times the capital C, which is the total heat capacity, which is the heat capacity per particle times number of particle. Okay, and times velocity, or the average velocity of your particle, and times mean free path. Okay, so remember this is classical thermal conductivity. So now we could use this standard definition of the kappa, which is proportional to the heat capacity, the velocity of particle, and mean free path. And we discuss both in the high temperature and the low temperature limit of the system. And then we could argue that the phonon contributed from the H3 term may give rise to observed behavior of the thermal conductivity in many solid state material. Okay, so let's take a short break. When we come back, we will study the high temperature, low temperature limit of this kappa. You could check our reference books on this normal and Umklapp processes of phonons and also thermal conductivity. It's pretty straightforward and standard formalism. But what you may not know is the link or relationship between the thermal expansion, thermal equilibrium, and H3. Okay, so we do need some scattering among those phonons, otherwise we cannot reach the thermal equilibrium. Let's just make a note on the mean free path. In the harmonic approximation, meaning we have only H2 or the second order in this Taylor expanded potential term, which account for this potential part of the harmonic oscillator. So suppose we have only the harmonic potential, then this mean free path is actually goes to infinity. Okay? So why? Because there's no mechanism for such a collision. There's no way that the phonons could actually collide with another phonon, which means that the phonons could live forever. Okay, so there's no way that the phonon can decay to either vacuum or to other phonons or different states. And this mean free path is actually finite, meaning less than infinity for H3, because there is a way that the phonon can actually collide. Okay, and this actually is very crucial to understand the collisions, or thermal equilibrium processes of solids. Okay, because the harmonic potential alone cannot explain the thermal equilibrium. So we need the collisions, because that's really what happened. So we'll use the fact that this mean free path for this n-harmonic term, such as the H3 term, is actually inversely proportional temperature. So we can expect the higher temperature, the more collisions that you can imagine, right? So if you reach the very high temperature, so that the kinetic energy of these electrons or ions are really enhanced, so that these phonons can actually collide with another phonon pretty easily. Okay, so you can imagine that this, roughly speaking, this, of course, this perfect 1/T behavior is another thing, but you could imagine that as you increase the temperature, you get more chance to collide between or among those phonons, and therefore the mean free path becomes shorter, right? So later we're going to use that empirical formula, and this is indeed consistent with the experimental observations for the mean free paths of ordinary materials. So let's just discuss different temperature limits of this kappa. So remember, this kappa is proportional to what? 1/3 of C, capital C, times V times L. So let's just look at first the low temperature limit. Okay, of course, the in general, in this quantum regime where temperature goes 0, this kind of a quantitative behavior of this kappa is still, roughly speaking, proportional to this heat capacity and velocity and mean free path. Of course, this, the prefactor may be different, but this kind of behavior is still obeyed. So in the low temperature limit, so we will discuss later that the scattering is actually very, very rare. So there are only some scattering at the boundaries. And meaning that the scattering length or the mean free path is actually, roughly speaking, at order of your system size, because that is, so we will define that in just a moment. So this mean free path is actually, almost a constant, and your kappa is actually, roughly speaking, proportional to capital C times velocity m times mean free path. And so the mean free path is almost the system size, capital D, which is a constant, and the velocity is also some constant in the 0 temperature limit, which is, roughly speaking, this Fermi velocity. And the capital C we know very well, which behaves T cubic, right? So from the harmonic term, that this specific heat goes like T cubic from this phonon, free phonon. Okay, so if you multiply this 3 factor, so you get T cubic behavior at low temperature limit of the kappa. And later we'll compare this kind of a quantitative expectations with the experimental observations. So next, let's look at the high temperature limits. So we haven't defined this normal and Umklapp process, but we will in just a moment. So this is U process, the Umklapp processes dominate. And this capital C, as I mentioned, this is 3 kb times n, which is almost a constant in the high temperature limit. And as we expect, this mean free path is actually inversely proportional to temperature, because the collision frequency is proportional to the number of phonons. And the number of phonons is proportional to temperature T. And as a result, this L is actually almost 1 over T behavior. And in this limit, kappa is proportional to capital C, which is a constant, and velocity, which is temperature to some power, which is somewhere between 0 and 1, as an exponent of this temperature dependence of velocity in a high temperature region, and this mean free path, which is 1 over T behavior. So if you multiply these 3 factors and collect only the temperature dependence, you get 1 over temperature to the power of x, where x is somewhere between 0 and 1. And these 2 extreme limits agree, these expressions of this kappa in these 2 temperature limits agree with the experimental observations. For example, for this sodium fluoride, and you'll see that there's a T cubic term at low temperatures, but 1 over T to the power of x behavior in the high temperatures. And the crossover temperature is about 10. And this is 50 Kelvin, and this is 2 Kelvin. So now you appreciate the power of these collisions, okay? Because we expect these collisions between phonons, and therefore we could explain this temperature dependence of the thermal conductivity for many materials. And so let's just define this normal and Umklapp processes more closely. So this is the interactions among these 3 phonons. So suppose that this arrows refers to the direction or the flow of these phonons with their momentum K1, K2, and K3. So by momentum conservation, the outgoing phonon carrying the momentum K3, which is the sum of this K1 and K2 as initial 2 phonon momentum. If this is satisfied, meaning that all the 3 phonons actually are moving along, roughly speaking, the same directions. Move, say, forward, the same direction. So sometimes we call this forward scattering, meaning all the 3 particles are moving along, roughly speaking, the same directions from the left to the right. Of course, their vectors are different, right? Because they have different components in, say, y-axis, but roughly speaking, there are no turning back. meaning, the scattered phonons still moves along the same directions as the initial phonons do, right? Okay, so that's the normal process, meaning, that's the standard or conventional scattering processes. But there's a Umklapp process which that's different. Of course, then it's not simply just a forward scattering anymore. So you can see very clearly that this K3 is actually moving backward. So let me just, initially this K1 and K2 phonon are moving from the left to the right, but this K3 phonon, which is a scattered phonon, moves backwards along the negative minus x direction. And sometimes we call this backward scattering because K3 now moves in the opposite directions compared to this K1, K2. And the reason why this K3 moves the backward direction is because of this reciprocal lattice vector G. Remember that. Okay, so if this reciprocal lattice vector G is finite, then we do have such a situation where this K1 plus K2 is actually K3 plus G, and K3 is actually backward with respect to K1 and K2. And very important point concerning this thermal equilibrium due to this scattering of phonons is this Umklapp processes. And this is crucial, critical, or important to the thermal equilibrium. And to also explain this thermal conductivity and thermal expansion and so on. So, let's take a short break, and when we come back, we will start to really link these Umklapp processes and this thermal equilibrium in solids, including more detailed description of this geometric scattering or, the boundary scattering of some phonons at the boundaries, and also the scattering by other phonons. And we will very more clearly explain to you the intermittent connections between these Umklapp processes and the thermal equilibrium. Okay, so let's take a short break. So you can find this plot, I think, in both the Kittel's first book, Introduction to Solid State, and also in Ashkurov-Mermion, and I believe I've seen this in Ashkurov-Mermion. So you could very easily find the corresponding chapters discussing this. But back then, when you learned this solid state 1 or introduction to solid state, you may not have studied these phonons, the second quantization and so on, and you don't know much about the energy momentum conservation and normal and Umklapp processes. Okay, but now you understand. So, which means that you are able to 100% understand everything mentioned in Introduction to Solid State. And these are the missing links in your introduction to solid state, which requires the second quantization. So let's just talk about the link between this H3 or phonon scattering and thermal equilibrium. As I mentioned, the mean free path can come from two sources. One is called the geometrical scattering or the boundary scattering, meaning the particle actually hits your boundary, and that lead to some scatterings of phonons at the boundary. So these are the phonons. So these are not the phonon-phonon scattering that we discussed here. It's simply just due to the boundary effect, because you have the finite size, so the phonon cannot travel over the your system side. So at the boundary, the phonon should actually, hit something. So that's called the geometric scattering. But the second one is more important, which is the scattering of phonons by other phonons. So remember, we discussed the harmonic potential, right, in the beginning. So if we consider only harmonic potential, then we have just the first geometric scattering present only. And there's no chance that phonon could scattered. So the phonon, even though cannot stay forever, but almost forever, because the phonon cannot scatter by another phonon. But for the anharmonic potential, we have both. And in particular, the second term gives us 1 over t behavior of the mean free path, which agrees with the experiments. So to reach the thermal equilibrium, we need both. In particular, we need Umklapp scattering processes. So now let's just analyze this, conclusions or derive such a conclusions in more detail. Suppose we consider the cubic term and the H3 term, which involves 3 phonon scattering, right? So of course we could consider H4 and H5 and H6 and so on, but the lowest order that would lead to such a Umklapp process is actually 3 phonon scattering, which was precisely what we just discussed. And to reach a thermal equilibrium, remember in your classical STEM Mag, you know very well that an object initially is actually heated up inhomogeneously, meaning that you have a hot end and cold end on the other side. Okay, so that is the initial state. But if you wait and wait and wait for a long time, then the particles that carry, the heat, more heat, will actually exchange thermal energies with the cold particles, so that the hot particles actually move to the cold, and the cold particles move to the hot end. So initially, you got T2 is actually greater than T1, but after this thermal float or exchange of your thermal float from the hot to the cold and from the cold to the hot, so that at the end of the day you get uniform temperature, the same temperature, and this is called thermal equilibrium. So that's what you remember in your elementary physics or general physics 1, that an object can reach the thermal equilibrium by exchanging such hot and cold particles. But imagine you cannot have such exchange processes, then there's no way that you could reach the thermal equilibrium. And the Umklapp process is the key to have such a kind of a backflow of a heat. So let's just draw some diagrams and you will note what I mean. Suppose that we discuss only normal processes, the M processes, which means that the K1 plus K2 is actually K3. So it is the 4 scattering. And we consider an object with a hot end and a cold end, or we call it phonon source and phonon sink. And this temperature is high and this is low, or cold end, hot end. Okay, so we know very well that these particles or the phonons inside the object can actually move from the hot to the cold, right? So if you calculate the particle flow, which is the number of particles Nk for any particular momentum state K times h bar k, where k is the momentum or the wave number. So h bar k refers to the momentum of that phonon, and you sum over all such processes. Of course, this k could be pointing to any directions. So initially, this is non-zero because you got a hot end and the cold end. The particles will flow from the hot to the cold, right? So if you calculate this particle flow or momentum flow, you get a finite value because of this heat flow, right? And let's just come back a little bit to this cartoon picture, which we could reach the thermal equilibrium. So when we really reach the thermal equilibrium, the number of particles that move from the hot to the cold is actually the same as that from the cold to the hot, and therefore, this particle float or this momentum float is actually got cancelled, right? So if you really reach the thermal equilibrium, and this net momentum float should be 0 initially or final state. However, if you look at this plot, if you consider only the normal processes where the particle can actually move forward from the left to the right, and there's no way that the particle can actually go back. So if there's only such processes available, then there's no way that J could be 0. So the conclusion is that if we have only this normal state, normal processes, and J, the net momentum flow, is always finite, no matter how long you wait, because you need the backflow to cancel the other float to reach really the thermal equilibrium where there's no net flow of particles. But the other direction is missing if there's only a normal process available, and therefore we reach the conclusion that this normal processes alone cannot lead to the thermal equilibrium. And namely, we need the Umklapp processes. So let's then discuss the Umklapp processes like what we defined, K1 plus K2. It's actually revert the direction of K3 because there is a reciprocal lattice vector shift G, so that's K1 plus K2 is actually K3 plus G. So let's just draw the same diagram here. We've got hot end and cold end. And of course, we have forward moving phonons, but since these phonons can actually scatter by other phonons, so there should be some phonons carry K3, which is along the opposite directions, right? I don't know which one, but there exists such Umklapp processes which lead to the K3 and point to the opposite directions. And as a result, even though the initial particle flow or momentum float is non-zero, but at the end of the day, when these Umklapp processes dominate, then the final momentum float should be zero. Okay? Because the forward momentum or flow momentum float cancelled by the backward. Okay? And as a result, you get really a thermal equilibrium reached. So which means that this justifies that this Umklapp process is really important, okay? Or the H3 process is really important, okay? Even though harmonic potential is enough to give rise to the phonon energy and so on, but to reach the thermal equilibrium, we do need the Umklapp processes, okay? And likewise, the thermal expansion is also X cubic term, the thermal expansion. This cubic terms in the potential will lead to the thermal expansion, which we don't have time to discuss, but you could read corresponding chapters in our textbooks. So I guess that's enough for today, and I think we finished the phonon chapter, and on Wednesday we will start a new chapter, which is electron-phonon coupling, and then we will derive the BCS theory of superconductivity for ordinary metals, and then at the end of the semester we will come back to the magnetic properties of solids. So now you get a full picture of the fermionic or electron Coulomb interacting system and also the phonon system. So now we should combine these two, and there is some peculiar phenomena associated with electron-phonon coupling, and this coupling is really essential to explain this, the superconductivity in ordinary metals.